Okay, thanks, Tim. So thanks to the organizers for putting together this nice conference, and yeah, I'm looking forward to a fun week. All right, so today I'll talk about work in progress with Saqib Hassan, who's a student of John Marsh Russell's at Oxford, and yeah, so this should be out, soon, hopefully in the next couple of weeks. So keep an eye out for it. Okay, so let me start with some motivation. So understanding the nature of quantum gravity in de Sitter remains a big important problem in our field. And part of this problem is understanding the spectrum of objects that can appear in de Sitter, which means understanding what sort of particles, strings, branes, their charges, etc., that we can get in a de Sitter quantum gravity. Because we're talking about de Sitter, top-down results can sometimes be difficult to come by. And this is why bottom-up arguments, for example, using black hole physics, can play an especially important role. And this is really the path that we will take in this talk. So one such example of a bottom-up argument is the Festina Lente bound. And I will say a lot more about Festina Lente in what's to come, but let me just give an overview. So Festina Lente means to hurry slowly, and the phrase refers to the evaporation of large charged black holes in de Sitter space. So this is a mouthful, so let me unpack it a little bit. So de Sitter space, unlike asymptotically flat space, has a horizon. And so there's a notion of a largest black hole that can fit inside of de Sitter. So if you start with a black hole and you start making it bigger, eventually the horizon of the black hole will coincide with the de Sitter horizon. And that is the largest black hole really that can fit inside de Sitter. So these black holes are called large or Naria black holes inside de Sitter, and they can be charged. It's just like black holes in asymptotically flat space. These can also be charged. So they are in some sense extremal, just like the Rice and Nordstrom black holes can be extremal. These ones are also extremal because two horizons are about to cross, and whenever two horizons cross, then we typically get super extremal solutions that have naked singularities. And because they are on the verge of becoming super extremal, one can expect to learn something by studying the evaporation of these black holes. Okay, so if we understand how these black holes evaporate, we may, for example, demand that they don't evaporate into becoming super extremal. And this ends up giving the Festina Lente bound. So I'll review the argument a bit more carefully in a moment. But if you just demand that these black holes can evaporate without becoming super extremal, then you get this bound, which says that which says m squared is bigger than GQ m Planck h. Here m is the mass of the charge carrier. So all charge carriers in de Sitter have to have a mass that obeys this lower bound. M is the charge of the mass carrier. G is the gauge coupling, of the U1 theory under which the black hole is charged. Q is some integer quantized charge. M Planck is the Planck mass, and h is the Hubble rate, which is related to the cosmological constant by square root in de Sitter, in this normalization. And so this bound should remind you of the weak gravity conjecture, and this is not a coincidence because really the logic is the same. In fact, Festina Lente was derived by taking the logic of the weak gravity conjecture and then applying it to these large black holes in de Sitter. In the context of weak gravity, we say that weak gravity requires the existence of particles whose mass is smaller than their charge, and this is exactly the kinematic condition that is required for extremal black holes in asymptotically flat space to be able to evaporate without becoming super extremal. Okay, so in flat space when asymptotic flat space we get this condition from requiring that black hole evaporation doesn't take them into becoming super extremal. And then in the de Sitter case, you get the condition that I showed in the last slide, which is this one. Okay, so this is some condition on the masses and charges of particles. The weak gravity conjecture, however, readily generalizes to extended objects, and so this has been done very early on too, and it also places an upper bound on the tensions of extended objects from also by similar arguments, for example. And so if Festina Lente is really to be the counterpart of weak gravity, but for these large black holes in de Sitter, then a very natural question to ask would be, is there a version of Festina Lente that also applies to branes? So far, the inequality I showed you on the previous page applies only to particles. And the question we want to answer is there a version that also applies to branes, just like the weak gravity applies to both particles and branes? Okay, and this is the question that we will answer in this talk, showing that, yeah, indeed, there is a version of Festina Lente that one can use for branes. Okay, so with this motivation in mind, this will be the plan for this talk. First, I'll start by reviewing Festina Lente with a little bit of more detail. And then I will talk about how it can place bounds on the tensions of branes in the sitter. We will consider two types of branes. The first ones will have gauge fields that live on their walled volume, and the second ones don't. And then we'll get slightly different bounds in both cases, but yeah, we'll see that. And then I will summarize and conclude. All right, so let's start with a review of Festina, but also feel free to ask me any questions. Yeah. Okay, so let me start by reviewing Festina Lente. So like I said, the big picture is we want to study the evaporation of these large black holes in the sitter, and you want to ensure that they evaporate without becoming super extremal. Okay, so we want to talk about charged black holes in the sitter. So the setup really that we want is some Einstein-Maxwell theory in the sitter space. So the theory is just like this. There's an Einstein-Hilbert term, there's a Maxwell theory, and then there's a positive cosmological constant. And so this is a very familiar theory, and we know its solutions. It has charged black hole solutions. So later on we'll add charged matter, but let's forget the charged matter for now. So this theory has black hole solutions, and they are parameterized by two numbers, their charge and their mass. And so the space of black hole solutions looks something like this plane. Okay, M is the mass of the black hole, Q is its charge. And these are really the cousins of the Reissner-Nordstrom black holes in asymptotically flat space. Okay, so here we're just taking the Reissner-Nordstrom black hole and putting it in the sitter, basically. So just like in flat space, we don't expect that all values of Q and M provide valid solutions. For example, in asymptotically flat space, we know that good solutions have charge less than their mass, like good black hole solutions have a charge less than their mass. And so good black hole solutions lie below this Q equals M line in asymptotically flat space. I'm showing it here by this dashed red line. So something similar will end up holding in the sitter, especially if you think about the limit where the mass is very small, so the black hole barely knows that it's in the sitter. But like I mentioned previously, in the sitter there's also a qualitatively different thing because the sitter has a horizon, and so really there's a cutoff on the mass. So the mass of black holes in the sitter cannot be arbitrarily large. So good solutions have to be to the left of this vertical line. So there is a vertical line, and good solutions have to lie to the left of this vertical line. So one can do this more carefully, and then you find that the actual region of good solutions, which don't have naked singularities, is the region inside this shark fin, which qualitatively captures these two effects. Okay, so black hole solutions outside the shark fin are super extremal in the sense that they have naked singularities, and those inside are good solutions. Now, we are familiar with this branch. The weak gravity conjecture talks about this upper branch, and it's the branch of extremal black holes. Their near horizon geometry is ADS2 times S2 in 4D. But then there's also a new branch, and Festina Lente is a statement about black holes on this branch. So weak gravity talks about the black holes on this top branch. Festina Lente is a statement about the black holes on this branch. Yes. Yes, I'm fixing those. Yeah. No, this is only the near horizon geometry. This is not the. This is only the near horizon geometry. So the near horizon geometry of these ones is ADS, but of these ones it's the sitter of these black holes, and right, and so Festina Lente is really a statement about these black holes, And for the rest of the talk, we'll only talk about this Naria branch, and we will mostly ignore the rest of the shark fin. So we'll talk about solutions that only sit on this Naria branch. One thing I want to point out is that this line curves to the right. And so if you actually start somewhere here and you lose charge too quickly, for example, by having very light charge carriers, then this black hole has a chance of becoming super extremal, because if you lose charge too quickly, then you can go outside the shark fin region. Okay. All right. So like I said, for the rest of the talk, we'll only talk about black holes on the Naria branch, and these have a de Sitter 2 times S2 geometry. And here I'm showing a picture of this de Sitter 2 times S2. So the de Sitter 2 has one time direction, which I'm not showing, and it has one spatial direction, which is the horizontal direction on the slide. And then there's an S2 multiplying this, which is represented by the vertical directions. Okay. When these black holes are charged, then they have an electric field, going in this de Sitter 2, and the magnitude of this electric field is just m Planck times Hubble. Okay, so the de Sitter 2 has horizons just like any de Sitter. So the left horizon here, you can think of it as the black hole horizon, and then the right horizon, you can think of it as the cosmological horizon. Okay, it's very easy to guess the magnitude of the electric field just by looking at the Lagrangian and then balancing the term with the cosmological constant with the electromagnetic field strength. Okay, so let's now think about the presence of charged particles. So in the presence of charged particles, these electric fields are unstable to the pair production of these charged particles. So you can produce positively and negatively charged particles in pairs, which screens the electric field, and then basically discharges the black hole, because the negative one, if this black hole is positively charged, the negative one will fall in, and the positive one will go outside, and this discharges the black hole. Okay, so this pair production is of course the famous Schwinger pair production, and the rate is proportional to this exponential factor, which is e to the minus m squared. M here is the mass of the charge carrier divided by the electric field. Okay, so this is the flat space rate. You can actually do this in de Sitter 2 and get the proper de Sitter rate. But the answer that we get in the end will not depend on these details, and so for simplicity, we'll just talk about the flat space rate. There's a prefactor here which is large. The prefactor here is set only by the electric field, and it's of order m Planck h. So it's large in the sense, it's large in the sense that every other process in this system, for example, Hawking radiation, or the way the black hole loses mass, is set by Hubble rather than m Planck Hubble. Okay, so m Planck Hubble is a much faster rate than just Hubble. On the Naria background, the electric field, like I said, is m Planck Hubble, and so this exponential factor ends up looking something like this. Okay, with m squared over GQ m Planck h. Now there are two regimes that one can think of. You can think of a regime where the charge carriers are massive, so m squared is much bigger than the denominator here, and this process is exponentially suppressed and is very slow. When this process is slow, then this black hole evaporates slowly, and you don't lose charge too fast. The black hole remains good. It doesn't go super extremal, and everything is okay. But there's a different limit when m squared is much smaller than GQ m Planck h. Now in this limit, you can't really use this formula, but you have to derive, you have to find the different equations that describe the evolution of the black hole. And in this limit, it turns out that this electric field gets screened almost immediately. So the time scale on which it's screened is set by the prefactor, which, like I said, is m Planck h. So the electric field gets screened, almost immediately compared to Hawking radiation. And in this limit, then you can find the evolution of the black hole, and it looks something like this. Yeah. So in this limit, when the charge carriers are very light compared to G m Planck h, if you find the equations that describe the evolution of this black hole, you'll see that the black hole ends up jumping, down here, and then which is a big crunch. So what you'll see is that the space-time evolves into a big crunch, and the interpretation is that the black hole has jumped down there. And yeah. Right. 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 Yeah. So. Right. Right. Yes, you're right. So this is a problem. Yeah. So this is right. So in here, I mean, in this, so here I'm just describing, the calculation of Miguel. Yeah. So I don't think they take into account, the same things, but really the effect that I think needs to be taken into account is basically the annihilation of these pairs that you produce. So once you take that annihilation into account, then the crunch actually happens by a singularity theorem. And so then there is not so then with back reaction or not, the answer should not be different. It's a theorem that's actually ensuring the crunch. Um, yeah, exactly. Yeah. Zero. Yeah. Right. So yes, the particle antiparticle annihilation I think should be important in getting this. Um, in any case, yeah. Um, okay, and so to avoid this, one must require that you're not in the limit, and so you're somehow in the opposite limit. The charge carriers have a mass that's bounded below by g times m Planck h. Okay, and so this here is the Festina Lente bound that I showed on slide 2 or 3. Okay, so now we finally come to branes. So the story is very, very similar. The big picture is, again, we want to study the decay of these large charged black holes in the sitter in the presence of branes and ask that they do not become super extremal via this decay mechanism. So really what was important in the other case that we could screen the electric field very, very quickly. So the screening of the electric field, really more or less is what gave this effect here. And so here we can see that branes can also screen the electric field. And we should expect similar bounds to Festina Lente too. Okay, so let's start with the first scenario. So let's consider branes that have this world volume action. So this is the action written in Euclidean signature. So the action has a tension term which wants to minimize the area of the brane. Then there's a coupling A wedge F. So E here, so A here is the bulk gauge field. So this is a field that lives in the bulk, and it's the same as it's the gauge field of the Maxwell theory that we had all along. But then in addition, we're going to assume that this brane has a gauge field living on its surface, and the field strength of that gauge field is FBR. Okay. So what this coupling means is that this brane can become electrically charged under A if there's a non-trivial profile of FBR on its surface. So if FBR has an expectation value on the brane, then you can imagine doing 2 of these 3 integrals over FBR, and you get an electric charge. And you get, you can find that a little area element of the brane is charged electrically under A. And so because it's charged electrically, it will be able to screen the bulk electric fields, just like um, the electron-positron pairs, of the previous discussion were able to screen the electric fields. So again, we'll compute, this nucleation rate in flat space. So here, I'm discussing two branes for now, but we will generalize to higher dimensional branes and higher dimensional, de Sitter later. So in flat space, if we start again with, we start with this geometry, and then we imagine, what does it take to nucleate a brane like this, and then you can compute the for a two brane, you can find the solution explicitly. So you find the solution of a two brane in addition to the solution for FBR, which is the field strength on the surface of the brane. And it turns out there's a solution where the top half, the northern hemisphere of the brane has a positive charge, and the southern hemisphere has a negative charge, and so somehow it mimics the pair production of E plus E minus pairs of particle antiparticle pairs. So you could compute the production rate for these branes, and you get an exponential that is very similar to the exponential that we saw before. The mass of the particle now is replaced by the tension of the brane, and there's an E in the denominator along with the coupling, so just like what we had before. Okay, again, the prefactor is independent of the tension of the brane. It depends only on the electric field. And in the absence of this exponential suppression, this process will be fast. It will be set by M Planck H compared to H. So then the same argument just goes through again. And so just like in Festina Lente, if we want to require that this process is not too fast in the sense that it's exponentially suppressed, then we get a lower bound on the tension of this T2 brane. Okay, so if you demand that this process doesn't happen too quickly in the sense that you don't nucleate too many branes, then you get a lower bound on the tension of these branes, which looks something like this. And it's similar in flavor to the Festina Lente bound. So either this is true, or the nucleated brane does not actually fit between these two horizons, and this gives you another condition on the tension, which is also a lower bound. So either this is true or this is true, and in general, T2 has to be larger than the minimum of these two. Yes. Yeah, so what happens is you nucleate this brane. It has a positive charge on one side, negative charge on the other, and it screens the field in between. No, it will expand. It will expand. Yeah, it will expand and eat up the electric field, which is what provides energy for the tension of the brane, for example, in flat space. Yeah, so the idea is that you create many of them. And then, yeah, but I mean, you only do this when the process is fast, so to speak, which really we cannot calculate in that limit. So the rate that you calculate is when it's slow, and then in that limit you actually calculate the nucleation of one brane only, and that will expand exactly. But then you want to ask that this process is not too fast because yeah, which then you imagine that you're creating many. So it's just like Schwinger. So in Schwinger you really Yes? This brane, yes. So, yes. Right. Yes. So, but it happens locally, so that it's really on one local point on the S. Yeah, that's true. Okay. Yes. Yeah. Exactly. And then the brane. Yeah, that's correct. Okay. And so if you demand that this process is not too fast, then you get a lower bound on the tension of the brane, which is it has to be higher than the minimum of this or this. Okay. There are of course order 1 factors that we cannot control, but yeah, but parametrically it should behave like this. And then you can do the same story with higher dimensional branes and higher dimensional de Sitter, and generalize it. For these branes, you have to generalize the coupling to something like this. and then you get similar bounds. So you get bounds on the tension, and one of them comes from requiring that the rate is slow, and the other one comes from requiring that the brane actually fits inside the de Sitter 2 spacetime. And you get the same thing here. These formulae, however, don't work for 3 branes and 4 branes. At some point, you have to invert this 4 minus p, and it shows up in the denominator, and so it doesn't work for for p is equal to 3 or 4. Okay. Yeah. So this is the first. Okay. So then in 1 minute, I'll tell you very quickly about this. So you can also imagine having a different kind of brane which doesn't have a gauge field living on its surface, but couples only through the bulk gauge field, and it has a coupling like this, like A wedge F. So the D branes of string theory are not like this; they are like the previous example that we talked about. But this one is like axion domain walls. So axion domain walls have a coupling like this, and what this coupling means is that this brane will become electrically charged in the presence of a magnetic field. Okay, and so it can play a role in the screening of fields around a dionic black hole. So if the black hole has both electric and magnetic fields, then you can nucleate these branes which can screen the charge of that black hole. So there's a very similar story here. You can just derive the nucleation rate, ask that it's not too fast, and then you get a lower bound on the tensions of these branes. So there's a caveat I won't mention here, but I mean, due to time. But then yeah. So this is discussed in the paper. So one last thing So one last thing I want to mention, like I said, these branes here are like the D branes of string theory. So the D branes of string theory have couplings like this. And what you can do is that you can ask, if I read off alpha from from the couplings of D branes, how does do these satisfy these equations or not? So this is some naive extrapolation because we're not really constructing de Sitter. We're just assuming that if the D branes of string theory remain there in any de Sitter construction, then what happens to these inequalities? And it turns out that all these inequalities are actually satisfied by the D branes in string theory, and they're satisfied in the same way, all of them. So they very often, this inequality is always saturated, and then this one is satisfied with ease because this one has a Hubble on it, which always ends up being much smaller than, which is much smaller than M string or M Planck. So the D branes of string theory satisfy these inequalities, even though we did not use string theory to derive them. Okay, and yeah, so that's all I have to say because I'm out of time. So let me summarize. So I presented a bottom-up argument as to why the tension of branes in de Sitter has to be bounded, and this is just a generalization of the Festina Lente logic. But there's still a lot more things to work out. So branes in string theory, for example, have other charges. They have other couplings, and one has to ask, how do these affect the story? So this discussion, some of these will be discussed in our paper too, but I'm sure we won't cover everything. You can consider generalizing to axionic black holes, and you can ask, what are the bounds for 3 and 4 branes? There are, of course, relations to other Festina Lente conjectures, etc. And one important question is whether there is any application to phenomenology, for example, early universe physics or de Sitter constructions or things like that. And finally, you can ask whether there is a similar bound for axion domain walls. And so this will also have some important consequences. Yeah, thank you so much for listening.